Jai Hind students, welcome to my YouTube channel. Students, life has two rules. Rule number one. I repeat students, life has two rules. Rule number one is never quit. This is rule number one. And rule number two. Always remember rule number one. So students, these are the two rules of life. Rule one is never ever quit. Rule two is always remember rule number one. So what actually I mean to say is that life has various ups and downs. At times you may feel low, but never ever think of quitting. Instead, we need to be grateful to the Almighty for giving us such a precious gift which is life. So life is there to be enjoyed. Life is there to be appreciated. So students, with that note, let's start today's session. In the previous lecture, we have discussed the method by which a galvanometer can be converted into an ammeter of a given range, isn't it? Now in this particular session, we'll try to discuss the conversion of a galvanometer into a voltmeter. Now, let me remind you, a galvanometer, what's the purpose of converting it into a voltmeter? I've earlier told you a galvanometer is a sensitive device. It can't be directly connected to a main circuit because it is very sensitive. So even when small current flows through it, it shows large deflection. So when connected directly, a galvanometer may eventually get damaged due to two reasons. First is the pointer of the galvanometer in an attempt to go out of the scale may eventually break. And second is, on passing large current, due to the production of heat, the insulation of the coil may get damaged and eventually the device may be non-functional, isn't it? So these are the reasons why a galvanometer needs to be converted into an ammeter and it needs to be converted into a voltmeter. So voltmeter, volt, that's the SI unit of potential difference, meter to measure something. So voltmeter students, it's a device which is used to measure the potential difference across any 2 points of a conductor, right? And there is DC voltmeter, there is AC voltmeter. Anyway, let's start with the topic. Let us consider a galvanometer which is given to us and it is offering resistance G, which is small. Galvanometer is itself a low resistance device. So let us consider a galvanometer. Let us consider a galvanometer of resistance G. And this galvanometer is to be converted into a voltmeter, right? And let Ig be the current. Ig be the current for which galvanometer shows full scale deflection. The galvanometer shows full scale deflection. What it means is Ig is the maximum safe value of current that can be passed through the galvanometer, right? And our objective is to convert this galvanometer into a voltmeter. Our purpose is, our objective is to convert this galvanometer into a voltmeter of range, say 0 to V volt. That is, we need to convert the galvanometer into a voltmeter which can read a maximum value of potential difference of V volt, right? So this is our objective. So for this, students, a very high resistance wire, it is to be connected in series to the galvanometer coil. So let me draw the diagram for you. This is suppose the galvanometer offering resistance capital G and a high resistance wire. This is an extremely high resistance wire, say R. This is a high resistance wire. It is to be connected in series to the galvanometer. Now, connecting this high resistance wire in series, the net resistance of the circuit will tremendously get increased. So the current will fall down to a safe lower value, so that the current flowing through the galvanometer is Ig. Ig is the maximum safe value of current. That is, Ig is the current for which the galvanometer shows full scale deflection. Since these two are connected in series, so the current flowing through each of the galvanometer and this high resistance wire must be same, right? So this series combination of galvanometer and high resistance wire, this constitutes a voltmeter. So this is it. So the point to be noted is, students, first, in order to convert a galvanometer into a voltmeter of range 0 to V volt, a high resistance wire, an extremely high resistance wire R is to be connected in series with the galvanometer coil. With the galvanometer coil. Right? And second is, as I stated, this series combination of the galvanometer and the resistance R constitutes a voltmeter. So, the series combination of galvanometer and high resistance wire offering resistance capital R constitutes a voltmeter. It constitutes a voltmeter which can measure a maximum potential difference of V. Clear, students? Now let us find out the value of this high resistance wire which is to be connected in series to the given galvanometer coil so as to convert it into a voltmeter. For that, students, the method is these two are connected in series and it's a voltmeter which can measure a maximum potential difference of V. Current in series remains constant, isn't it? So the same current is flowing through the galvanometer as well as the high resistance wire. So the current, as we are aware, it's given by potential difference across the ends divided by the net resistance across those 2 points. So what's the net potential difference across these 2 points? It's V divided by net resistance across these 2 points. These two are connected in series, so net resistance would be G plus R. This is the net resistance. It's very simple. So the net current flowing through the series grouping of galvanometer and the high resistance wire is Ig. It's equal to V divided by G plus R. So let's try to rearrange the terms, right? So what we do is, we can cross multiply it, Ig, G plus R, it would be equal to V, or G plus R, it would be equal to V over Ig. Therefore, students, the value of the high resistance wire, it would be equal to V divided by Ig minus capital letter G. So this is the value of the high resistance wire which is to be connected in series to the given galvanometer coil so as to convert it into a voltmeter of range 0 to V volt. Right? So this is the formula to be remembered. Okay, next point. Now let us find out the net effective resistance of the voltmeter so obtained. Now since these two are connected in series, so we have to make use of law of combination of resistances in series. So the resistance of the voltmeter, it will be given by G plus R. This is the net resistance of the voltmeter so obtained. Clear, students? And we are also aware in series the resultant resistance is always greater than the value of the individual resistances. What I mean to say is that resistance of the voltmeter must be even greater than the resistance of this wire, which is itself very, very large. So resistance of the voltmeter must be greater than the resistance offered by this wire, which is itself a high resistance wire. So what's the conclusion then? A voltmeter is an extremely high resistance device, right? So this is a very, very important conclusion. A voltmeter is an extremely high resistance device. High resistance device. Its resistance is even greater than this high resistance wire, right? So students, what about the resistance of an ideal voltmeter? What about the resistance of a perfect voltmeter? Obviously, for a perfect voltmeter, for an ideal or a perfect voltmeter, the resistance must be approached towards infinity. Clear, students? The voltmeter, which is a perfect one, it must offer infinite resistance. So remember, ammeter is an extremely low resistance device. An ideal ammeter should offer zero resistance, while voltmeter is an extremely high resistance device. An ideal voltmeter possesses infinite resistance. So, if you are supposed to write the resistance offered by the galvanometer, ammeter and voltmeter in a sequential order, either in ascending or descending order, then it should be like this. Resistance of the ammeter, it is extremely small. Ammeter, it offers almost zero resistance, it is almost negligible. So it is less than the resistance offered by the galvanometer, and it is less than the resistance offered by the voltmeter. So this is the order. So the resistance of the galvanometer lies between that of the resistance offered by the ammeter and that of the voltmeter. Clear? So there's an important concept, students. A voltmeter, while we connect it in a circuit so as to measure potential difference across any 2 points, it is always to be connected in parallel, right? We will try to find out the reason for it. As in the previous lecture, I have suggested that whenever an electric device is to be connected in an electric network, then it is to be connected in such a manner that on its introduction in the circuit, it shouldn't alter the current flowing through the circuit. Even if you connect that electric device either in series or in parallel, it should be connected in such a manner that the current flowing through the circuit should remain constant. If current through the circuit remains constant, then the potential difference across any 2 points on the conductor, which will be IR, that will also remain constant. And it is only in this case that the true value of the potential difference can be measured by that measuring device. So always keep that in mind, right? So let's try to find out why a voltmeter is always connected in parallel. A voltmeter is always connected in parallel. Okay, let's try to find out the reason for it. Look, students, this is the main circuit, suppose, and current I is flowing. and suppose this main line offers R, and these are the 2 points A and B where the potential difference is to be measured. So what will be the actual potential difference? Actual potential difference between the points AB would be equal to I multiplied by R. R is the resistance offered by this section AB of the conductor, right? This is our objective, to measure VAB. Now, what we need to do is that we need to connect the voltmeter in parallel like this. This is the symbol of a voltmeter, V. This voltmeter is to be connected in parallel. Now look, the resistance offered by the section AB is R, while the resistance offered by the voltmeter is RV. This will act as a junction. The main current flowing through the main circuit is I. This is I. This point will act as a junction. So current will get divided in these 2 branches. This is one of the branch and this is the other branch. Right, students? Now look, voltmeter, just now we have discussed, it's a device which offers almost infinite resistance. An ideal voltmeter possesses infinite resistance. So, if this branch offers infinite resistance, or for that matter, very high resistance, then it will draw negligible current through the main circuit. Because higher the resistance, smaller will be the current flowing through that branch. So since RV approaches to infinity, therefore, the current through the voltmeter would be almost 0. That is, a voltmeter when connected in parallel, because of its extremely high resistance, it draws negligible current from the main circuit. So that on connecting the voltmeter in parallel, the current in the main circuit more or less remains constant. So since no current, almost negligible current flows through this branch, therefore the current through AB almost remains same, II, it remains same. So now this device can give the actual measure of IR, which is the true value of the potential difference between the points A and B. So again I repeat, students, whether you connect ammeter or you connect voltmeter, these are the measuring devices which are to be connected to an electric circuit in such a manner that the current flowing through the circuit must remain more or less same. That is, the current through the circuit must remain constant. So that is the reason why ammeter should always be connected in series, because it is an extremely low resistance device. And voltmeter should be connected always in parallel, because voltmeter being high resistance device, when it is connected in parallel, it draws negligible current from the main circuit. So that the current flowing through the main circuit more or less remains constant. And as a result of which, voltmeter when connected in parallel across any 2 given points will be able to give the actual value of the potential difference between those 2 points. I hope you have understood this concept, students. So there is a very basic and very important question which can be asked even in your Viva during practical examinations, right? Why an ammeter is connected in series and why a voltmeter is always connected in parallel. So that's it, students. We have completed this topic of conversion of galvanometer into a voltmeter. So I hope you have understood each and every concept. So just remember, in order to convert galvanometer into ammeter, a low resistance wire is to be connected in parallel to the galvanometer coil. While in order to convert a galvanometer into a voltmeter, a high resistance wire is to be connected in series to the given galvanometer coil. Ammeter, it's an extremely low resistance device. Ideal ammeter possesses 0 resistance. Voltmeter, it's an extremely high resistance device. The resistance of an ideal voltmeter is infinity. Clear? And this is the order of the resistance of ammeter, galvanometer and voltmeter. So students, that's the end of the theoretical portion of magnetic effects of current. In the next lecture, which will be the last lecture of this particular unit, we will be discussing some numericals based on the moving coil galvanometer sensitivity and conversion of galvanometer into ammeter and conversion of galvanometer into voltmeter. So do join me in my next lecture then. Thank you.